All right, ladies and gentlemen, 2 o'clock. Welcome back to your favorite class. I feel like if I say that enough, maybe you'll actually believe it. No, just kidding. We all know it's your favorite class. Okay. First thing you'll notice, I have no hair. You guys are stressing me out. No, I'm kind of going for that prison look because, well, I feel like I'm in prison. So I had my roommate, aka my girlfriend, cut my hair, and now it's all gone. Okay? I'm much more aerodynamic now. And as an aerospace engineer PhD, I approve. Okay, continuing. Announcements for the class. Your homework number 4 was due today. Hopefully you turned it in. If not, what are you doing? Turn your homework in. Next announcement. Your second exam for the class is this Friday. It will be just like the previous exam. I'll hand it out online, by email, and on Blackboard. You'll do the work in front of you on scratch paper. Take a picture when you're done. Send it to me by email, just like last time. All right, worked really well last time, so we'll keep that going. Next announcement. I was going to include momentum on this second exam, but instead of trying to squeeze it all into like 2 days or 3 days that we have this week, I decided that I'm going to move it back to the next exam. So this second exam will only have work and energy, which is what we did last week, and kinetics, which is what we did 2 weeks ago. So information regarding or related to homework number 3 and number 4. Kinetics, work and energy. There'll be 2 problems on the test. 2. Okay? They'll be a little bit more involved because those problems just end up being a little bit more involved. So I think 2 questions on that second exam is actually going to end up being the appropriate amount. So there you go. 2 questions on this upcoming exam. Make sure you study work and energy and kinetics. In addition, I have posted practice exam problems for you guys. And since you don't have any homework to really work on right now, you can work on those. Okay? I've posted the solutions as well as the problems. So go do that. Okay. The way I see this week going is today and tomorrow we'll introduce momentum topics. Thursday, then I'll do exam review by kind of going over some of the practice problems from that practice exam sheet that I handed out, or the practice problems that I handed out. And then Friday, you got your test. So that's the way that this week is going to go. Any questions? Straight away. You'll get a homework on momentum later. Don't worry. I know you're wondering. Am I going to get to do momentum problems? I'm really excited about it. But don't you worry. You'll still get to do them. I know you were worried. The hair, says Aaron. Thanks. Thank you. What hair? Okay. If there's no further ado, which you all know, I hate ado, we will begin the new topic, which is conservation of momentum. So lecture notes have been posted. You can take a look at those. I hope you guys liked my meme today. It's very mathy. The 0 to the 0 power, she's looking sad because she's equal to 1. And the 0 divided by 0, he's like, don't look at me. I'm confused. Okay. What am I? I don't know if I'm 0 or infinity. It's hard to say. All right. Onwards. New topic. And that is conservation of momentum. Not to be confused with conservation of energy, which we did last week. So this week, new topic. Conservation of momentum. All right. You guys all saw conservation of momentum in your particle dynamics class. So I'm done. See you guys next week. Just kidding. Conservation of momentum. We talked about it for particles. You should have learned it for particles. We're going to extend it to rigid bodies. Just like we've done basically everything else in this class, you've understood something about a particle. Now we have to talk about a collection of particles, which is a rigid body, and how this sort of works now with a collection of particles. So let's quick review what you should have learned in your particle dynamics class. Okay, so we'll review. Particle momentum. And I'm going to start here with Newton's often neglected first law. We talk a lot about Newton's second law, but we'll start here with Newton's first law. And that first law is that an object in motion will stay in motion unless acted upon by an outside force. terrible writing. Unless acted upon by an outside force. So this is kind of the basis for the momentum that we're going to talk about in the next couple of days, and even it'll bleed into next week. Think about a hockey puck on an ice hockey rink. If I push that hockey puck along the ice hockey rink and there's no friction, I mean, we're assuming ideal conditions here, there's no friction between that puck and that ice, well, that puck's just going to move along that ice infinitely until it, hits the wall or something else stops it or something else pushes it. Okay, that's kind of the way that the ice is designed to work in a hockey rink. All right, it's kind of the beauty of that particular sport. So you talked about this general idea in particle dynamics with maybe this like hockey puck analogy, where you've got this particle moving along the ice and then there's some impulse or some force that changes its momentum, its linear momentum, and now you have a new linear momentum. And that's the idea behind conservation of linear momentum. Okay, so consider particle of mass m with initial velocity v1. So the picture you should have in your head is some particle of mass m, and it's moving with velocity here, which is v1. Usually when we talk about momentum, we're talking about the linear momentum. And if you recall back to our sort of definition of momentum, that momentum is the mass times the velocity. So we'll sort of write this as mv1, right? And I'll get rid of that m because it's included in this mv1 definition. All right, so this is my initial momentum for my particle. Specifically, this is the linear momentum, mv, right? Now, if I want to change the direction, I need to provide some force that acts on this particular piece, right? So you should have learned that if you want to change the direction of this guy, you can add to this particular momentum what's known as an impulse, okay? So if I add to this particle some jolt of force over some small amount of time, so let's say that I'm going to add to this a force over a short amount of time. So I will add to this an impulse, usually written as IMP, from position 1 to position 2. So I'm changing my state of my particle from some initial linear momentum in state 1 to what will be some final linear momentum in state number 2. And generally for linear momentum changes, we have a force acting over a small amount of time. So here, this is an integral over some short amount of time, let's say t1 to t2, of the force acting on the object integrated over time, right? The final result will be the particle having a new linear momentum along a path sort of, which is a combination of the original momentum plus this impulse that you gave to it. Okay, so our final particle will have some final momenta, right? So here, this is final momentum, which is defined as the original mv1 plus the impulse that I had. And this impulse is in fact a vector, so we should treat it as such with a bar over the top. Hard to write in bold on this particular pad. So my resulting final momentum is something like the same mass, assuming mass is conserved, v2. All right, so this is kind of pictorially what's going on. We have some initial momentum, just here. We have some final momentum, which results after the impulses I put on it. So initial momentum, final momentum, and we'll label this as our impulse. Right. Mathematically, you can kind of see what's happening here. So we have a linear momentum plus an impulse giving us a final momentum. We would write this as written in math speak, what would be mv1 plus imp 1 to 2, where this should have a bar over it because it's a vector, equal to mv2. 2, where this imp 1 to 2 is the impulse vector. Oh boy. Given by the integral of the force that you apply, or that is applied, over time from t1 to t2. Time doesn't necessarily have to be short. It could be a long impulse. So I don't really have a good example off the top of my head, I guess, but if maybe a car is sliding along the ice and you need to move it, it's going to take you a pretty long time and a lot of force to redirect the momentum of that car because it has a lot of mass. So this time doesn't necessarily need to be short. All right. Here in rectangular components, you may be more comfortable writing the components, which would be the impulse from 1 to 2. Written in components would be something like still integrating from t1 to t2, but here now we have the various components, fx I hat plus fy j hat plus fz k hat, all this integrated over time. So that's your typical Cartesian definition. I think people are a little bit more comfortable seeing it in components because people understand force broken up into components. All right. So this is all generally for a particle. All right. This is your governing equation, or what should have been your governing equation for particle motion in 2002. Okay, so for particles. In 2002. Were you even born in 2002? Yikes. I don't know. Some of you in diapers, probably. All right. That's for particles. What do we do in this class? Well, we extend what we know about particles to rigid bodies. So that's what we're going to do. Which we remember, these rigid bodies are collections of particles. Now, because they have additional volume, we don't just talk about conservation of linear momentum, but we'll also have to talk about conservation of angular momentum. So let's quickly have a recap on what is linear and angular momentum of a rigid body. So they have both linear momentum and angular momentum, and both will be conserved. And they're both conserved at the same time. Imagine that. Now, we call our definitions of linear momentum of a rigid body. So linear momentum given by what we saw as the capital letter L is typically what we use for linear momentum. So the linear momentum of a rigid body, and various points will have different linear momentum on a rigid body. We know this because not all points on a rigid body have the same velocity. So let's specify here that like the linear momentum is given by, let's say here, Lg, which is the mass of the particular rigid body times velocity g. All right, this is the linear momentum given by here, and this is at center of gravity, or the center of mass of the object. Similarly, we had a definition for angular momentum. That was given by not L, but we used the letter capital H, G. And here now not mvg, but ig omega. All right. And this angular momentum is again about the center of gravity. So if we think about sort of looking at all of the momentum components of a rigid body, and all of like the impulses that might act to give us a final momentum, we're going to have an analogy that looks a lot like this analogy for particles, except that we can do a very similar thing now for rigid bodies. So we'll have some initial momentum, we'll have some impulses that occur, and we'll have some final momentum. And not only will we have linear momentum, but we'll also have angular momentum and angular impulses which act. All right. So what we're going to do now here is we're going to draw what is commonly called an impulse momentum diagram. So we'll draw our first rigid body impulse momentum diagram. Okay. So it's going to be analogous to this particle impulse momentum diagram. There's an initial momentum, there are some impulses, there is a final momentum. So we're going to have that same general idea. First is our initial momentum. All right. Here's my potato, my beautiful rigid body that we're all accustomed to seeing here. It has a center of mass or center of gravity here at the middle, which is given by capital G. And this rigid body at the center of gravity will have not only velocity at the center of gravity, but also some angular velocity as well. So the initial momentum for this particular guy might be, in a linear sense, this general direction. So here we have the mass of this rigid body times the velocity of this rigid body at the center of gravity. And we'll say that this is in state number 1, right? This also has angular momentum, which if this is sort of rotating about the center of gravity, then the initial angular momentum will be Ig omega, and this is state number 1. So we have some initial angular momentum, we have some initial linear momentum. Right? We can modify that linear momentum and that angular momentum by adding linear impulses and angular impulses. So we're going to add to this impulses. All right, here's my center of gravity again. And these impulses don't necessarily have to act at the center of gravity. They can act anywhere, all right? And the impulses that you're probably most familiar with are like these force impulses. So we could have some forces that are acting over here. I don't know, this is the integral of F1 dt. Here's impulse number 1. Maybe we have a force over here. So here's the integral F2 dt. But not only could we possibly have impulsive forces, we could also have impulsive moments, right? So if I, let's say, had a torque wrench and I was sort of torquing on the object, and I just kind of give it this one of these like rawr kind of torques to it, okay? I could also have some random, let's say at this location over here, some positive integral of m dt, which is occurring. All right, so this is an impulsive moment. We'll talk about those in just a second. This is going to lead to a new linear and angular momentum in state number 2. So this will be equal to what is the final momentum, which is here my body, my rigid body. And maybe now with these forces and these moments that have acted in this impulsive manner, we have a new direction for our linear momentum. So here this is mvg condition number 2. And maybe it's like slowed down a little bit. So here this is Ig omega position number 2, and that G should be a capital G. All right. So hopefully we see the analogy here is that, okay, for a particle, there's this hockey puck sliding along the ice. We give it a little push in some direction, some force over time. It redirects that linear momentum. You can have the same idea with some potato, all right, some large rigid body. It's moving along in a linear fashion. We give it a force, we give it a nudge, and it moves in a new direction. Same idea. We could have some object that is spinning, and it would spin in this configuration indefinitely until something stopped its spinning. And then all of a sudden we apply some moment on it to slow it down or speed it up. All right, so we can slow it down or speed it up by applying some moment over some amount of time, and now it's moving slower. Or if we applied a moment in the same direction it was spinning, we could spin it up. All right, so that's the general idea there. So let's put some math down to this, since we've sort of drawn our picture so nicely. So mathematically, just like we do for kinetics, it's easiest for us to do our analysis at the center of gravity. The equations aren't so stringent for conservation of momentum as they are for like kinetics and conservation of energy, but still, in my opinion, it's easiest to kind of keep your analysis focused on the center of gravity. All right, so still focus analysis at center of gravity, and I'll say usually. Not as stringent a requirement, and we'll see some situations where our analysis is easier at places that are not the center of gravity a little bit later. But for now, let's just go with that. All right. So for a rigid body, with center of mass or center of gravity at G, we know that the sum of the forces about point G is equal to the mass times the acceleration at G, which we'll also define as the summation of the forces being the total reaction force at G. So here this is total reaction force. So you may see the sum of the forces written as capital R, just as one vector. This is all of the forces that are added up together, kind of reconfigured at point G. And this, we know, can be written as sort of the second form of Newton's second law, which we talked about before, is the first derivative of the momentum with respect to time. All right, so another alternate definition we have. Or if we write the linear momentum using capital L as linear momentum, these are all of our forms of like the sum of the forces as MA type looking equations. All right. Here's your general like Newton's second law. All these guys here is Newton's second law, which will become the basis for our conservation of momentum. So if we want to sort of look at this guy, we could look at it mathematically by rearranging to, we have here RG is equal to dm vg dt, which is dlg dt. The idea here is we could kind of cut this guy out and integrate with respect to time to get the following equation, and that is that let's go through it fully. I was going to kind of cut some corners, but let's go through it fully. So we'll integrate the left-hand side from T1 to T2 of the reaction forces that occur at the center of gravity, dt. This is equal to the integral from T1 to T2 of the change in linear momentum vector with respect to time. All right, well, the change in linear momentum vector with respect to time integrated over time. Well, this is first fundamental theorem of calculus. So simplify. And you'll end up with the integral from time number 1 to time number 2 of the reaction forces on the object. These are external reaction forces acting over time. The integral from T1 to T2 is Lg evaluated at T2 minus Lg evaluated at T1, right? Or more commonly, we might just write this as LG in state number 1 minus LG, sorry, in state number 2, minus the linear momentum at the center of gravity in state number 1. All right, I'll bring this LG to the left-hand side by adding both sides with LG, and you'll end up with sort of the final form of linear momentum, which we're all kind of accustomed to or seen before, and that is the linear momentum of the object at the center of gravity in position number 1 plus the integral from T1 to T2 of the reaction forces that are acting on this object externally at point G integrated over time equal to the linear momentum about the center of gravity in situation number 2. This is your conservation of linear momentum for a rigid body. Okay, this is analogous to what you saw for particles, like mv1 plus integral of f dt equals mv2. It's a very similar idea. All right. Now let's look at the angular conservation of momentum. Okay, we're going to have to recall what our definition of angular momentum really was. All right, and by Newton's second law, we can still have this general relationship where the sum of the moments at the center of gravity is Ig alpha. Okay, you've seen this before. You just did a lot of it on your kinetics homework. This is also equal to, let's call the sum of the moments equal to some moment reaction. So if we're taking a bunch of little moments that are added up on all of our object, the sum of those moments, let's just call a reaction moment, which is m sub r. So this is a summation of all of the moments that are acting on the piece. This is equal to the derivative of the angular momentum term, which we know as Ig omega with respect to time, which is also equal to the derivative of what we know as the angular momentum vector about the center of gravity, hg dt. Okay, I'm again going to kind of bring this down and rearrange. So again, we can pull, like, let's say r here, and we'll take hg here. All right, these two guys, and you'll end up with the reaction moments equal to the derivative of the angular momentum with respect to time. Just like we did for linear, we'll integrate with respect to time. And let's say our time domain T1 to T2. Okay, then we're left with the integral from T1 to T2 of the reaction moments, which is the summation of all the moments, integrated over time, equal to the integral from T1 to T2 of this derivative of the angular momentum with respect to time, integrated over time. All right. Again, we're going to enact first fundamental theorem of calculus. Right. So simplify. And you'll have a very similar situation to what we did for the linear form. That is from T1 to T2 of the moments acting over time integrated over time. And here, first fundamental theorem of calculus, we'll have something like hg2 minus hg1. So this is the angular momentum about the center of gravity at time number 2 minus the angular momentum of this object at time number 1. Again, I'll rearrange by pulling hg kind of to the left-hand side, and you'll see the most traditional form of the conservation of angular momentum for a rigid body, which is hg in state number 1 or time number 1 plus the integral T1 to T2 of the moments that are acting at the body at the center of gravity, dt, equal to the angular momentum of this object about the center of gravity at time 2. Here is your conservation of angular momentum for a rigid body. All right, both of these conditions must be met. We must obey the law of physics. Rawr. Okay. So angular momentum 1 plus the moment impulses equals angular momentum 2. Pretty straightforward. I'll say must be executed at mass center or at a fixed point of rotation. Similar to the kinetics problems, we have to sort of do the analysis at a fixed point or at the center of gravity. There are complicated mathematic reasons why we have to do that I don't want to go into right now. Just believe me when I say I want it that way. Okay. Backstreet Boys reference. Do you know the Backstreet Boys originally debuted 23 years ago today? Do you know that? Now you know. I'm a big Backstreet Boys fan. It's my favorite music. Just kidding. You guys probably don't even know who that is. All right. So must be executed at mass center or at a fixed point of rotation. Let's look at some alternate forms of that, because these guys, yeah, they're nice generic mathy forms, I guess. But let's look at some more alternate forms that'll be a little bit easier to actually like do analysis with. All right. Alternate forms. All right, let's start with the linear momentum. All right, which we saw was LG1 plus integral of R dt is LG2. Well, we know LG is just mvg. So that means we could rewrite this as mvg1 plus integral on R, these are our reaction forces, dt equals mvg2. I'd say this equation here is much more common to see in practice. The theory equation is nice, but this equation here is much more common in practice. And you know the difference between theory and practice. They're the same in theory, but not in practice. All right. So that's mainly your only alternate form you're going to see for linear momentum. And it looks just like the form that you had for particle dynamics, except now here we've focused on the center of gravity. Okay, so we see these G's here. We've focused our analysis to the center of gravity, which is an important distinction. When you're doing this for a particle, you're always at the center of gravity because there's no volume of the particle. So particle physics is the same. All right, let's look at alternate form for angular momentum. Okay, and we kind of have two here that are common to use. And so we know the general form is hg1 plus integral of the moments that are acting, the reactive moments, equal to what is hg2. All right. Now we have kind of two alternate definitions that we've seen in the past for angular momentum. right? So recall the two definitions that we saw in the past for angular momentum. That we had, the angular momentum was ig omega. Oh, that's not a vector. Silly me. Ig omega. And we also saw that the angular momentum was the moment arm r crossed with the linear momentum, which is r cross the linear momentum L. This was our original definition of angular momentum, which we also know to be r cross mv. All right. So let's take a look at the alternate forms with these two guys as alternatives. We'll have something like, instead of hg, we'll have ig omega 1 plus integral of mr dt equals ig omega 2. All right, so that one is used fairly often. We'll see this one quite a bit in this class. And we'll actually also see this other alternate form pretty often as well. And that's because a lot of times we're given velocity components about particular pieces. And so kind of doing this cross product R cross MV is sometimes a little bit easier for us to work with. So the other possible alternative that you might see is position vector crossed with MV1 plus integral of, you might see it as R, since we're kind of doing this sort of cross F. This, remember, is a moment. dt equal to, what is R cross MB situation 2. So these are your other two sort of alternate forms of the angular conservation of momentum equation for rigid bodies. How are we doing out there? We awake? Beautiful day. I want to go outside. Don't go outside. Looks like I got a question. Someone got a question. The Hair. Was that your jam in 2002? Dude, I'm in the band. Didn't you know Kevin? He's in the band. Okay, this is my jam. JT ended up kind of taking over with NSYNC. They kind of duked it out for a while there. NSYNC, Backstreet Boys. JT kind of won out on that sort of battle. I'm more of a jazz fan myself, personally. Let's move on. Kind of talked about this, and so I'm going to pass over what's on the next slide. If you're kind of following along with this slide, is the momentum diagrams. And these are going to be the basis for analysis, right? So I'll just say here the momentum diagrams. So usually, momentum diagrams are helpful for analysis. So if I go back up to, wow, way up there, this guy. This is your momentum diagram. Initial momentum, impulses, final momentum. We will be doing a lot of this. Don't worry. Don't you worry your little keister. We'll be doing a lot of those guys. All right. So see the notes if you want some additional examples for how to do this. All right. Do I have time to do this? Yes. All right. So let's do a practice moment diagram example. I will bring a picture in here and we will execute the moment diagram. All right. Here's our setup. We've got a block sliding along and it's got velocity v1. It hits this pin here at O, or this sort of like lip in the ground, and causing it to sort of pivot into sort of an upright configuration. All right. So initially, velocity v1, hits point O, and begins to pivot. All right, Ross approved pivot. We want to figure out what is the angular velocity of the block as it rotates around O. That's what we are going to try to do here. All right. First things we want to do is create a moment diagram for the situation. It'll help us with our analysis. So let's do that. And we'll include both linear and angular components to help us on our way. All right. So hopefully we sort of understand the problem here. This guy is sliding along this general direction, minding his own business, when all of a sudden he slams into this point down here at O. All right. That's going to cause this guy to sort of prop into this upright configuration. So I want to know during this motion here, what is the angular velocity that's sort of being incurred by this block? So that's kind of the analysis that we're doing at this particular point. So let's do our moment diagram, our momentum. All right. Got to scroll this down a little bit. Hopefully you kind of got the problem statement down. I'm gonna move on with my life here. Hopefully you got it down. If not, it's in the notes. Initial momentum. We need an initial momentum. We need an impulse. And we need a final momentum. All right. The initial momentum is easy. This block sliding along the ground with a certain velocity. So here's my initial momentum of this block. Center of gravity, G. It's moving to the left. Here, it's got a mass, it's got a velocity, situation number 1. I'm done. There's no rotational motion of this guy, so I don't have any angular momentum of this piece at this particular moment. All right. The linear momentum is just mv1. All right. Impulse. Here's where things start to get a little bit tricky. All right. The impulse is now, I will have this block running into point O. The way that we're going to deal with this is we're going to treat point O as a pin. All right. So treat O as a pin. If we're treating it as a pin, that means it can provide force on this block both in 2 directions, right? So sort of in the Y direction and in the X direction. Obviously, it's going to be pretty easy to see that it's going to provide some resistance in this X direction. So here, let's draw that. And I'm going to label this, well, let me give it the red. I'll give it the red. The red pen of death, right? I'm going to label this as the integral of the force that O provides in the X direction over time. I don't know how long necessarily that impulse is taking, but I know that point O is providing some force in that particular direction over some amount of time, though I don't exactly know what it is. It's also doing the same thing in the Y direction. All right. I've got the impulse of the force at point O in the Y direction acting over time. Good, great, wonderful, fantastic. Those are the impulses that are acting on this box at that particular time. Then, in situation number 2, complicated. I'm going to sort of draw this right after it has released from the ground. Okay, so imagine that there's a very small space between the box and where it has released from ground. I mean, I could even like write this on here if you want. Okay, so here we are again at point O, kind of in the lower left. All right, it's kind of an important point for us in this particular problem. And we also have our center of gravity of this guy here at point G. Now, what we know is that if we're going to be pivoting about point O, and point O is kind of being treated as a pin, then my box is going to be pivoting around that particular point. Okay, so if I want to think about what the motion of the center of gravity is going to be here, it's going to be like fixed axis rotation about point O. Okay, so here's like the radius to get out to that particular location, and it's going to have sort of a circular path around that point. All right, pretend that that's a circle. It's going to rotate up with this circular sort of path around that particular point. So if I want to know what the velocity of that particular point is, or I want to know what the linear momentum component of this particular piece is at that particular time, I know that the velocity is going to be tangent to that path, and I know that I still have the same mass of my object. So the linear momentum in this particular situation, after the block has struck the wall, is here, mv2. Right? I can sort of determine what the angle of this velocity is going to be using some geometry. So this angle here is the angle I'm making with the horizontal, and I'm going to call this, I can call it whatever I want, but let's call it the Greek letter phi. Phi, phi, pho, fum. I smell the fingerprints of scum. Ace Ventura, When Nature Calls 2. Great movie. Let's define our geometry in our box. So go back up here. See, we have short side length B, long side length C. That means that this angle phi is the same as this angle here, phi. This short side is the length B. This long side is the length C. So I can define the angle B using the inverse tangent. So note here that tangent of phi is simply B on C. So if I want phi, that's the inverse tangent of this thing. All right. That will help me define the orientation of the velocity in this problem, just simply based on the geometry of the box. All right. Last thing we'll do is we'll define our last angular momentum component, and that is we're now going to have some rotation of this guy around point O. We got some angular velocity now. So we have to define for ourselves now this IG omega. And if we want to be complete, since we're doing a momentum diagram, this is in state number 2. Right? So there's your IG omega in condition 2. And understand that this is in like the K direction. All right, so this is your full momentum diagram for this particular problem. All right, that's going to be it for now. We'll call it here. And we'll pick up this example tomorrow to kind of finish out solving for that angular velocity in state number 2. All right, thanks for coming. First Ace Ventura is better. I agree. Number 2 got a little crazy. Little too. Flipping the Jeep 6 times, landing in his parking spot. Come on. That's ridiculous. Still some good scenes, though. Like a glove.